due to the visa problem. And the second paper, unfortunately, is also about the truth discovery in called sensing system. But this paper, study a totally different issue about the truth discovery. The title of the paper is Cloud-Enabled Privacy-Preserving Truth Discovery in Cloud Sensing System. Still a joint work with my students and colleagues, Chengli Miao, Wenjun Jiang, Yaliang Li, Suxin Guo, Zhan Qin, Houping Xiao, and Professor Jing Gao, and Professor Kui Ren. Like I mentioned in the previous talk, thanks to the proliferation of all kinds of the mobile sensors as well as the human sensors, the cloud sensing has drawn significant attention in recent years. However, the cloud sensing in nature are human-centric sensing paradigm, so it has a fundamental problem, which is the privacy. As you can see, so in cloud sensing applications, the cloud users, collect sensory data and upload their sensory data to a central server, like this. However, before the cloud users upload their sensory data, they may have some privacy concerns. They may be worried first whether the cloud server is trustworthy, whether their sensory data may be disclosed to other participants, and because the truth discovery method running on the cloud server can also output the reliability degree of each user, so the user may be also worried that whether the other people can know his reliability degree. Another concern maybe is also about the communication channel, whether the communication channel is secure or not, whether some other people can eavesdrop the communication between the cloud users and the cloud server. And before these privacy concerns can be addressed, the users probably are not willing to update their sensory data. So the user have such kind of privacy concern because the sensory data, in many cases, contain sensitive personal information of the users. For example, to evaluate the effect of some new drugs or medical devices, we want to collect the health data of the patients. However, such kind of the health data may contain sensitive personal information. And also, geotagging usually can provide us with accurate localization of some objects or events, such as the litter or pothole. However, the data collected by the participant may contain some sensitive location information. And also, in the application of the cloud wisdom, so we send questions to the users, and the answers provided by the users for some particular questions may contain some sensitive personal information. On the other hand, the user's reliability degree is also a sensitive information in many cases. First, we may be able to infer some personal information regarding the user from his reliability, such as the education level, the major, or even the age and the gender. And also, actually, so in some practical cloud sensing applications, the cloud server pay money to the users for their sensory data. And the price of the data is usually decided by the quality of the data. So if the users know the reliability level, they may be able to maliciously manipulate the data price. And unfortunately, existing truth discovery approaches fail to consider the protection of the user privacy. So in this paper, we aim to address this problem. We make use the homomorphic crypto system and propose a cloud-enabled privacy-preserving truth discovery scheme called PPTD. And our goal is, first, we still want to conduct the truth discovery task So the first goal is to discover trustworthy information for each object or entity. And at the same time, we want to ensure that each user's observation value, as well as his reliability degree, should not be disclosed. Let me first provide an overview of our scheme. First, the users observe the objects and report their observations to a central cloud server. And during this process, so our proposed PBTD protocol is actually composed of two different phases corresponding to the two phases in the general truth discovery process. The first one is the secure weight update process, and the second one is the secure truth estimation phase. And during this process, during both of the two phases, actually all the operations are conducted on the encrypted data. So this way, we can well preserve the privacy of the cloud users. And these two phases actually are repeated until convergence. And finally, the truth can be outputted by the cloud server. And here, as you can see, we have a couple of the assumptions. Our first assumption is that all the parties in this cloud sensing system should be semi-honest. In other words, they are honest but curious. They will strictly follow the protocol we designed, but they will try to infer the personal information of the users through the intermediate result they received. A second assumption is that the users will not collude with each other to attack the system. Before I get into the details of the proposed method, so I'd like to first introduce some preliminaries. So let me first provide a review of the truth discovery procedure. Like I said in the previous talk, the truth discovery procedure is composed of two different phases, the weight update and the truth update. And the weight generally can be calculated using this formula. Here, f is actually a monotonically decreasing function of the distance between user's observation and the truth. This is very intuitive because the longer distance between the user's observation and the truth, the lower weight should be assigned to this user. And for example, we can use this function as the f function. And regarding the distance function actually is different for different types of data. And for continuous data, we can use the squared distance normalized by the standard deviation of the observations regarding the object M. And on the other hand, for categorical data, so actually we can use a binary vector to represent the observation of the users. Here, so if the user believes that the observed object belongs to a particular category, it will set the corresponding element to be 1 and the remaining element to be 0. So this way, we can still use the square distance as the distance function. And during the truth update phase, we can use this formula to update the truth. As you can see, this is actually the weighted average of the user observations. And next, I'd like to introduce the cryptographic tool we used in this paper. We used the additive homomorphic encryption method. Generally, if a cryptographic scheme can be said to be additive homomorphic if this scheme has these two operators that can satisfy these two homomorphic properties. And in particular, we use the widely used homomorphic encryption method, which is the PT threshold failure crypto system. And under this system, actually, as you can see, encryption of the summation of two different numbers is actually equivalent to the product of two encrypted numbers. And on the other hand, the encryption of the multiple of a number is actually equal to the exponential of the encrypted number. So how to decrypt the ciphertext? And here, as you can see, this Paleo cryptography system is actually an asymmetric cryptographic method. So we use public key to encrypt the data. And on the other hand, we should use a private key to decrypt data. But here, the decryption part is a little bit tricky because we first divide the private key into different pieces, and we distribute each piece of the private key to a particular user. And so each of the user actually has a private key share. And each of the user can use his private key share to decrypt the ciphertext. And he will have a partial decryption of the ciphertext. And if we can combine any T out of the total P partial decryption, so we will be able to recover the original plain text. So let's first look at the secure weight update phase. So, like I said in the previous talk, the weight of the user can be calculated using this formula. And here we use this K to denote the distance between user K's observation and the estimated truth. And according to the Paleo cryptography system, actually the encryption of the user weight can be calculated using this equation. And here, in order to calculate this encryption, so we need to know first the encryption of the logarithm of the total distance of all the users and the encryption of the log distance of user K. And how to achieve this? The cloud server will first send the estimated ground truth to each of the users. And this truth is actually derived in the last iteration. And in the first iteration, actually, this truth is randomly initialized. And after each user receives the estimated truth, he will be able to calculate the encryption of this distance to the ground truth. And it can also calculate the encryption of the log distance. And here we should note that the Paleo crypto system actually can be applied only on the integer numbers. But the distance and the log distance are usually fractional values. And here, so we'll first round the fractional value with a rounding parameter L, and L here is a magnitude of 10. And each user will forward these two ciphertext to the cloud server. And the cloud server should calculate the encryption of the logarithm of the total distance. Here the problem is because the distance is encrypted in the ciphertext, so how to calculate the total distance of all the users? And here we design a secure sum protocol to achieve this. The secure sum protocol is used to derive the plain text of a summation of the encrypted value provided by each user. As we can see, the user will first encrypt its own value and send the ciphertext to the cloud server. And the cloud server will first calculate the encryption of the summation using the cryptography, the Paleo system. And then it will send the ciphertext to randomly selected T-1 users. And after each of these users receive the ciphertext, it will try to decrypt this ciphertext. And because each user only have part of the private key, so it can only derive a partial decryption. And each user will send the partial decryption back to the cloud server. And because cloud server itself also has a partial decryption, so altogether it has T different partial decryption. So he will be able to decrypt the ciphertext and get a summation of the user values. And let's get back to the secure weight update phase. Another problem is that, so like I said, previously, when we deal with continuous data, so we also need to calculate the standard deviation of all these observations of the user regarding a particular object or entity. So to achieve this, each user will first send the encrypted observation to the server, and the server will calculate the summation of the observation using the secure sum protocol. And so it can calculate the mean of the observation. And the mean value is returned to the user so that the user can calculate the square distance between his or observation and the mean value. And it will encrypt it, this distance, and send it back to the cloud server. And the cloud server will first be able to calculate the summation of the distance using the secure sum protocol and finally derive the standard deviation. And here we should note that, so here standard deviation for each object only need to be calculated once. Okay, so let's get to the second phase, which is the secure truth estimation phase. Here, so what each user currently have is the weight, but in the ciphertext. So in order to calculate the truth, for each of the object using this formula, which is actually the weighted average of user observation, we need to first calculate the summation of the user weight. This part is pretty straightforward. We can simply apply the secure sum protocol. And the challenge is how to calculate the weighted summation of user observations. Still, so after each user receive the encrypted weight, it will try to calculate the weighted observation. And this calculation actually is different for different data types. And for continuous data, it's kind of straightforward because it can directly apply the Paleo system. This is equivalent to the exponential of the encrypted weight. However, for categorical data, so this part is a little bit tricky. Like I said, so the observation of the user for categorical data is actually a binary vector. And in this binary vector, so some elements, most of the elements are 0, and there's only one element which is 1. So if element is 0, actually we multiply 0 by a number, we still get 0. So this is equivalent to calculate the encryption of 0. However, so if the element is 1, and in theory, actually, when we multiply 1 with number, we still get this number. However, we cannot do that. If so, the user will derive actually encryption of the weight, and it will send this encrypted weight back to the cloud server. But the cloud server can compare, the message, the ciphertext it sent to the user and received from the user. It will find out that these two ciphertexts are the same, and it will be able to infer that this element is 1. So we cannot do this. So what we should do? Here, we can see that actually the weight, the number weight is actually equivalent to the weight plus 0. And according to the Paleo system, this is equivalent to the product of the encrypted weight and the encrypted 0. And here, because when we encrypt a number using the Paleo system, I'm not sure whether you notice this part. So actually, a random number is involved in this encryption process. So each time, the user will pick a different random number. So each time the encryption, the ciphertext would be different. So although we encrypt the same number, which is 0, we will get a different ciphertext. And the user will send the weighted observation, back to the cloud server, and the cloud server will be able to calculate the summation of the weighted observation using the secure sum protocol, and finally it can derive the ground truth. Okay, so let me summarize, the aforementioned two phases, and here I like to provide a complete process of the proposed privacy-preserving truth discovery protocol. So this protocol takes as input the observation provided by the cloud users, and it can output the estimated ground truth as all the existing truth discovery schemes. And first, the cloud server will send the estimated ground truth to the users, and the user will calculate the encryption of distance and the encryption of log distance, and send these ciphertext back to the cloud server. And the cloud server will derive the encryption of the logarithm of total distance, and finally it can derive the encrypted weight and send the encrypted weight back to the user. The user will derive the encryption of the weighted observation, and after the cloud server receives this weighted observation, it will be able to calculate the summation of the weighted observation and finally derive the ground truth. And these two steps, these two phases will be repeated until convergence. And finally, the cloud server will be able to output the estimated truth. So in order to handle the explosive increase of the cross-sensing data, so we actually parallelize some operations on the cloud server. And actually, because compared to the weight estimation phase, the truth estimation phase consume much more computation time. So we use the MapReduce framework to parallelize the truth estimation phase. Okay, so let's move to the performance evaluation part. We use the Paleo crypto system, and we set the key size as 512. And here the baseline approach we use is CRH. CRH is a state-of-the-art truth discovery method that can deal with heterogeneous data types. However, it takes no action to protect user privacy. And next, I'd like to introduce some metrics we use to evaluate the accuracy. Still, like I mentioned in the previous talk, we use the MAE and the RMSE to measure the error of the continuous data. And for categorical data, we use the error rate, which is defined as the percentage of the mismatched values between the estimated truth and the ground truth. The first experiment is conducted on a crowdsourced indoor floor plan construction system. This kind of system is used to automatically construct indoor floor plan from the sensor data collected from the smartphone users. And in this experiment, so we focus on a particular task of the floor plan construction system, which is to estimate the distance between two particular locations in a hallway. And this can be done by multiplying the step count and the step size of a particular user. And this is, of course, the continuous data. And in this experiment, we recruit 10 volunteers, and we measure the 27 hallway segments. We first studied the accuracy. as you can see here, so compared to the baseline scheme, the additional error of the proposed scheme is actually introduced by the rounding parameter. So actually, we studied the accuracy, under different setting of the rounding parameter. And as you can see in the figure, so when the rounding parameter L is large enough, and in particular if it's larger than, I think, 100, so the proposed method can achieve the same level of the accuracy as the baseline scheme. We also measured the estimation errors under different number of the users. And in this case, we fixed the value of the rounding parameter L to be 10 to the power 10. And as we can see in the figures, when the number of the users are increasing, so actually the error is going down. So this is very intuitive. So the more users, participate in the crowd sensing task, the more information we'll be able to get, and it's more likely for us to derive more accurate information. And also, we can see that the proposed PBDD scheme can achieve exactly the same accuracy level as the baseline scheme. And we also studied the convergence of the proposed scheme. In this case, we actually try different initializations of the estimated truth, and we use this objective value, this formula, to calculate the objective value. And as you can see in this figure, so no matter how we initialize the objective value, the proposed scheme can converge within a couple of iterations. And we also studied, we also measured the computational cost on the smartphone. And these two figures show the experimental result. And as we can see, in this case, the running time of the proposed method on smartphone is still within the acceptable range. And we can see in this figure, the running time actually is a linear function of the objective number. We also measure the computational cost on the cloud server. As we can see here, so actually the truth estimation phase actually dominates the running time, on the cloud server. So this is the reason why we want to parallelize the truth estimation phase. And also the running time is actually a linear function of the objective number. We also measure the computational cost, with respect to the user number. Still, we can see that this running time is linear with respect to the user number. And we also measure the energy overhead on the smartphone. Here we use a metric which is the average energy consumption percentage. It's defined as the energy consumed by the proposed PBTD scheme divided by the total energy of the smartphone while it is fully charged. And as we can see in this figure, so compared to the total energy of the smartphone, the energy consumed by the proposed scheme is actually negligible. The second experiment is conducted on a cloud visitor system. Oh, sorry. Okay, so in this task, in this application, we integrate the cloud answers and the opinions to a set of questions. And we set questions to the cloud users and aggregate their answers. And of course, the answer here are categorical data. And we also studied the accuracy of the proposed scheme still, so it's exactly the same as the baseline scheme. And we also measured relative error of the user weight. As we can see, when the rounding parameter is large enough, the error becomes negligible. And we also studied the computation cost on both smartphone and the cloud server. So on the smartphone, actually, the calculation of the weighted data actually dominates the consumption of time here. And on the cloud server, so the truth estimation so consume much more time than the weight update phase. So let me quickly conclude this paper. So in this paper, we studied the issue of the privacy protection in cloud sensing system and propose a cloud-enabled privacy-preserving truth discovery framework, PPTD. And the key idea of the PPTD is to perform weighted aggregation on the encrypted data of the users using homomorphic encrypted system. And during this procedure, the user observation values and his reliability score are protected. And in order to process large-scale data efficiently, parallelized extension of PPTD is also proposed based on the MapReduce framework. Okay, so this is the end of the second paper. So thanks for your attention. So I'd like to take questions.